All right. Is that everyone who's here? So everyone else is doing the thing. So anyway. Okay, all right. So so yeah, like pendulum assignment or like praxis alpha, whatever that means, or what. Life goes on. We are in lecture 3, in fact, of week 9 already. So the end is near in a way, as is the exam, of course. I wasn't planning to do a quiz, but there is a worksheet. While you're doing the worksheet, I'll set up a quiz so that the people who are here or on the stream can get something out of this. Apart from the lecture, which is going to be good as well. So we're going to be talking a little bit about iterating while modifying a list more. So something you shouldn't do, but nevertheless, sometimes you see other people do. We're going to talk about how to fix it, and we're going to be talking about the memory model. That's going to be, not the last lecture about the memory model, but there's going to be half a lecture more in 180, and then you'll hear more about it in 190, where it's even more important. Hello. So, okay. So is Discord complaining that there's no stream? No, Discord is nerd facing me for it. Okay. So that's fine. So the first thing I want to do is talk a little bit about iterating while modifying a list. So I'll do an example that should be robust. So here's the example. So we have, numbers. They don't happen to be increasing, actually, just numbers. And let's say that we want to remove the numbers that are greater than 5. And one way to do it, or one way to attempt to do it, rather, is to say, well, for num and numbers, if you find a number that's greater than 5, remove it. Okay? So if you run this, oh my God. It did work again. I did try it. Yes. Okay. So if you run this, yeah, it's a little bit unpredictable, but now I've gotten it to work. So it did not remove all the numbers that are greater than 5. Okay. So how could that be? So how could it skip the 12? Well, essentially what it's doing inside, it's getting like the next number from the list numbers. And then if you change numbers while you're going through it, it's not guaranteed that it won't get confused about the list shrinking and getting exactly the next element, except instead of the next element that it was supposed to give you, but then everything shifted. So the reason this is kind of unstable, and I messed it up again, is that on different computers can be a little bit different. But the point is, you're modifying the list while iterating. That is dangerous and a little bit unpredictable. Make sense? So does it make sense that this is not intuitive, that this should be what it is? Questions? Okay. Yeah. So the question was like kind of random. The answer is like, it's not random at all. The computer does the same thing every time. It's just that it's different depending on different versions of everything. So it's like predictable. It's going to be the same thing when I run it again. It's just not necessarily going to be reproducible exactly. Okay. And the lesson is, maybe don't do it. So how would I get a list of numbers that are greater than 5 in numbers without modifying numbers? Yeah. Yeah, exactly. And that's the usual thing. So make a new list, you said, and that's exactly the thing that you should do. Like instead of modifying the list while iterating over it, just modify a different list. So num's less than 5 or something. And now, proudly and without problem, you say, if num is smaller or equal than 5, then append it to num's less than 5. And the modified list still has the 12 for whatever reason, whereas the correct list has the correct thing. Okay. So, hey. Here's another thing that we might try. And again, I tried it on a different computer, but let's say that they have the same numbers. So sometimes it's going to work, sometimes it's not, but I'm going to try it. So I'm just going to try to empty the list numbers. So I'll say for num and numbers, and I'll say numbers dot remove num. That might work. That did not work at all. Okay. Yeah. Yeah, you could. Yeah. So same a little bit again. I'm not gonna even predict what it's gonna do. But yeah, so that did not work at all. So why did it not work? Again, it has this list numbers, right? So like 1, 2, 6, 3, 7. And for num and numbers, it's trying to serve up the next number and prepare to serve up the next one. And then what happens is you've removed the 1. So you'll notice that the 1 has been removed. And then it's already preparing to serve up the next one, which it thinks is element number 1 from the list numbers. But now element number 1 from the list numbers is 6. So for that reason, it's going to keep going. All right. Does that make sense? So to your question, how can you do it? So let's do it with pop. So L.pop returns and removes the last element of L. So if L is 5, 6, 7, you can say L.pop, and that would be return 7, and L is 5, 6. Make sense? So if I run this, it is now 5, 6. Okay. So one thing that you might want to do in order to empty this list is to say something like while length of L is greater than 0, L.pop. Make sense? So that would work because that is not really iterating over the list using a for loop. It's more like saying like keep removing elements, check if length of L is greater than 0. If it is, okay, remove another element, and they don't care which, right? Check again, is it empty yet? If not, yeah. Well, I mean, like we are yeah, we're not iterating through the list, like we're iterating over the list in some sense. Yeah. Yeah, exactly. Well, it's not so much depends on the length. I mean, although it does, but we're checking every time. Are we done yet? If we're not done yet, we remove another element, right? So that works. And yeah, like in some sense, like if you want to like go back to my like dictate of like never iterate over a list where I'm modifying it, well, in some sense, it's kind of sort of like doing that, but it's not really. So what we're talking about is using a for loop or a while loop using something from the list and then modifying it as well. It's not as if it doesn't ever work. It's just that it's not worth it. Okay. So don't do that. If you see buggy code and you see something like this, so like something like line 18, just say no. Just say, I'll rewrite it. I'm not going to even try to figure out what it does. Because, again, not worth it. Yeah.
Will it always like skip over like the
no, this is like not defined behavior. So there is a thing in programming languages called undefined behavior. So undefined behavior is, stuff like this, where there is no specification that actually tells you what's going to happen if you do something like that, and Python could just do whatever. So this is an example of that. We'll see much more important examples of that in ESC180. Okay, so no, like I don't believe there is any Python spec that actually tells you what's supposed to happen if you do that. After the fact, we can try to explain. Okay, make sense? So, okay. So that was like that. So the same lesson applies to dictionaries once you get to project 3, which has dictionaries in it. Again, just not worth it. The approach that you suggested is the right one, which is you want to do something like that, just create a new list and just, do your thing with a new list. That's all fine. One last question that has to do with what we've been doing before. So why are we emptying the list in the first place? Because couldn't you just say L is equal to the empty list? So how are 28 and 29, how are they different from 31? Anyone? Like, why not just do 31? Yeah. Exactly. 31 is creating a new list, whereas lines 28, 29, for example, are modifying the contents of the existing list. So when would it matter? How would we, let's say, a question on the exam, good question, actually, maybe I should have asked it on the exam, but let's say a question on the exam is saying, write code that would make it so that this works differently from this. How would we approach this? So over here, I want to write some code, and then I would choose whether to run this or to run this. And I want code here and code here such that it matters whether I do 30, 31 or 33. Any ideas? Yeah. 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 Okay, let's do that. So for example, L1 is equal to L. And then what do I do over here? Yeah, exactly. So I'll change either L1 or L, and I'll check whether the other one has changed essentially, right? So L now is empty. So what I'll do is like L dot append pendulum. Yeah. Okay. It's funny in context. So let's try it. So let's say that L is the usual thing, like brush teeth, like the usual thing that you do, attend ESC180, and stuff like that. And then what you want to know is whether pendulum is going to be appended to L or L1 or both. Make sense? So I'll run this. And then I'll run this. So most people in the class, right, removed the tasks from the list. And then we do L dot append pendulum. So now we can check L1. And L1 also has pendulum that was appended to it. Let me write it out twice. So I'll just copy this over here. And I'll print L and L1. And then I'll do the same thing here. So I'll do, So I'm just setting things up so that I run either this guy or I run this guy. And otherwise, I do everything the same way. Make sense? So if I run it like this, I have two lists, both of which have pendulum in them. And that's because L and L1 are aliases. So when I'm emptying out L, I'm also emptying out L1. And when I'm appending to L, I'm also appending to L1. On the other hand here, L1 has their priority straight. Make sense? So questions about what's going on here? So here, when I'm saying L is equal to the empty list, what I'm saying is L used to be an alias of L1, and now it's not. Right? So that means that if I modify the contents of L by appending pendulum to it, I've modified the contents of L, which is now the empty list, to have pendulum in it as well. Right? This is in contrast to here, where when I was emptying out L, I was also emptying out L1 because L and L1 are the same list. And then I appended pendulum to L, and that means that pendulum was also appended to L1. So let's look at it in Python Tutor, which actually has nice visualizations. So here, L is visualized like this list, right? So brush teeth attend ESC180. And then we're saying L1 is equal to L. So L and R1 are aliases. The way it's visualized is with L pointing to this list, brush teeth attend ESC180, and L1 doing that as well. We're now emptying out L. So pop means the last element goes. Pop again means the last element goes. And now both L and L1 are referring to an empty list. We're now saying L append. So that means that over here, pendulum is going to get appended. And now we're printing L and L1 while they're the same list. Make sense? So kind of as far as which one is better, kind of the memory tables or this kind of thing, I think the memory tables give you the real picture. But I think that once you're used to the memory tables a little bit, looking at those kinds of diagrams is maybe quicker. I just do it in my head usually. The way I do it in my head is I basically have those kinds of diagrams in my head. But when you're starting out, I feel like there is it's possible to explain the rules for kind of where the arrows point, but the way you explain the rules as well, it's what the table says. So we're doing some kind of combination of both. For that reason, different things might work a little bit better for this or that person. So, try both. So let's look at what's going on here. So edit the code. Okay, so now we have the same deal at first. So L and L1 are referring to the same list because L and L1 are aliases. And now we're saying L is equal to the empty list. Remember the rule. On the right-hand side, you have a new thing. You put the new thing in memory, and then wherever you put it in memory, the empty list, L is going to refer to that. In graphical terms, that means that the arrow from L is now going to point to something different. It's now pointing to the empty list. Make sense? So now when we say L append pendulum, pendulum is going to be appended here. And that means that L and L1 are two separate lists. And when we print them, two separate lists are going to be printed. Yeah.
Another list can also make the empty list and then append pendulum to L. Would the other one also change?
No. So the question was, what happens if you say, if I understand it correctly, like what happens if you do this, right? And the answer is this is a new empty list. So you can have multiple lists which are different. This might be slightly confusing because we reused memory spaces for immutable objects, right? So sometimes, not always, when there are immutable objects that are equal to each other, Python chooses to place them in the same memory cell. That is because they're immutable. They cannot be modified anyway, so aliasing is not an issue. But lists, of course, can be modified. So that means that you cannot try to save space by, storing an empty list once and then saying, well, all empty lists are the same. Well, they are the same until you change one of them. Make sense? Yeah. Yeah.
How when you the rather change the contour that it is already
Correct. How the off changes the content of
L is equal to an empty list assign a new list to L.
Yes.
That's completely different than the list.
That's correct. So the distinction that you're talking about is between things that's a good thing to talk about now. So things that change the variable versus things that change the contents, right? So what changes the variable? LHS is equal to something. That changes what LHS is. Whatever LHS was, it gets overwritten. Because that's what it means, like LHS is equal to the right-hand side. It means whatever LHS was before, we're overwriting it. Things that change the contents are things like L at 0 is equal to something. So that changes L at 0, but L is still the same list. You just change the first element of it. Things like L.pop, which is not saying L is equal to something. It's saying L is, so it's just saying basically like remove the last element of L. Right? So that's kind of what we've seen so far, actually, is those kinds of things. We maybe seen insert like briefly. Make sense? Yeah. So we're not really, I mean, yes, what we had is correct, but we don't really care about it. Like, forget about trying to read stuff. Okay, that's no problem. This is not the worksheet, it's nothing. That those wrong. Okay. So I want to get back. Want to get back to part D of U7 from 2022. All right. So let's do it with Python Tutor. I'm just copy and pasting it into Python Tutor. So here's how it's visualized here. So we're saying L is this list. So it has, 1, and it has the list to 3 as the second element. So this is element 0. Element 1 is this list. And basically, it's the address of the list. The way it's visualized here is using this arrow. And then the last element is 4. So that's over here. So now what happens when we create a copy of L1, essentially? So here we're saying L1 is L, so slice from the beginning up to the end, which means create a new list where the first element of the new list is equal to the first element of the old one, second equal to the second element of the old one, so on, right? So what happened is we now have an L1, which is a separate list, is its own list, and its first element is 1. Technically, it's the address, but it would be annoying to visualize this way. So if it's an immutable object, it just puts the value here, and it puts the value here. But the interesting thing is that element number 1 of L and element number 1 of L1, they're both the same list. And the reason they're the same list is we said like L1 at 1 is equal to L at 1. That's what creates an alias. So that's what we've done last time. Are you with me so far? Questions? All right. So now we're saying L at 0 is equal to 7. Thank you. Thanks very much. All right. So L at 0 is equal to 7. So this means that this is going to become 7. This guy doesn't care. Right? L at 1 at 0. So L at 1 is here. So it's really this list. So L at 1 at 0 is here. So naturally, if you change this, L1 does care. Because L1 also has this list as the second element. Right? So now we're saying L1 at 1 at 1. So L1 at 1 is this. L1 at 1 at 1 is this. So that's the same. Changes this guy. And now we're saying, print L, print L1, and there like that. Make sense? Questions about this? All right. So what we're gonna do, now is we are going to do one more slide, and then we're gonna do the worksheet, and I'll set up the quiz for you so that you can do it. Okay. And for anyone on the stream, that's fine. So anyone with the pendulum though. Okay, let them get the marks in physics. Okay. So calling a function. So here's how it basically works. if you have a call to a function, what happens is it's as if you said the local variable x is equal to y. Everything else proceeds as before. So it's just like as if you had this kind of statement. Does that make sense? So let's go back to my table. Do a quick example. Summarize this file. Okay. Now that's AI got mad. Okay. All right. So I'm taking this. Creating a new document. Expecting that you'd create a new document along with me. So we have our memory table and we have our variable table. We'll now have a new memory table variable table, sorry, once we call the function. So let's start with just what we had. So let's say that we have something like this here. Make sense? So when we say y is equal to 1, so let's say that 1 is here, and I'll like preload a few things. So maybe it's like this. So let's say that we say y is equal to 1. What does it mean? It means that in the variable table, we say y is going to correspond to at 1024. We're now saying z is equal to f of y. So what does it mean? It's as if we said local x. Oh, I switched those, sorry. So I think this is x, and this is y. So just so that it corresponds to the slides. Sorry about that. Or maybe not. Anyway, I'm going with this now. So local y is equal to x. Right? So how do we do that? So ordinarily what we would do is we would say like this is y and we're copying this over here. But the y is a local variable. So a local variable is going to exist in a different variable table. So that's going to be the locals variable table. So this is going to be local. And initially it's going to be nothing. And then we're saying the local y is equal to x. So what that means is we're taking this guy and we're copying it over here. And this is the y. So each function, while it runs, has its own local variable table. That is what allows us to have a global variable named x and a local variable named x at the same time. They actually live in two different variable tables. Make sense? So, okay. So now when we say, sorry, this is meant to be like this. So now when I say y plus equals 2, that changes, of course, the local y. So that becomes 1120. But x does not care. X is still at 24. The local y is what changed. And then what we're saying is return y. So that means that we're copying this guy over to z in the global variable table. So now we have a z here. And that is at 11:20. Make sense? So what happens, I'll keep this when you say print ZY. Anyone? Yeah. Yes, it's an error because there is no variable Y in the global frame. Right? So that's an error. What happens, however, if you say print ZX is you print Z, which is 4, because F computed 4, and you print X, which is still 1. Right? So X is 1, we never multiplied X. We multiplied the local variable Y, but that's different. And Z, oh, sorry, 3, of course. Okay. This was actually 3R all along, you guys. Okay. Sorry about that. Long week. Okay. Does it make sense what I did? Yeah. So why is Y at 11:20? So Y starts out as X. So Y starts out as 1024, meaning it's equal to 1. And then we add 2 to Y, so it becomes 3. So 3 is 11:20. Well, that was, yeah. Okay. Is that making sense? Yeah.
Where is Y starting at 5:20?
Y starts as Y equals 1 because we're saying f of x. X is equal to 1. And here it's as if we're saying Y equals x when we're sending this x to the Y. Okay. Does that make sense? All right. What other questions? All right. I'll give you, oh yeah. So after the function ends, it's not so much that it would clear the Y, it's that the local variable table is just not going to be accessible anymore. So clear refers to like maybe like, do you actually clear that memory? And the answer is, well, ordinarily, no, you don't. It might get overwritten pretty soon if you call another function, but usually it exists unless for security reason you decide to wipe it. So it's more that it's inaccessible than that it's gets like cleared in some sense. But as far as the programmer in Python is concerned, it's the same, right? Okay. Exercise A on the handout, please. And in the meantime, I'll set up the promised quiz just for my friends. And talk to your neighbor. If you haven't been talking to your neighbor for some reason up until now, this is a good time. Do the quiz. Yeah. All right, 3 minutes left. So hello. So let me do exercise A, and then we'll do B and C on Monday. Or maybe just C and then B as homework or something. So we have M is equal to 6, and we have N is equal to M. And then we have M is equal to 5, and we have F of M and we have print M like this. So I want, with your permission, to pre-store 5 over here and 6 over here. So we're not worried about it. So what happened? So the Y here, it's not here. The table actually doesn't exist. They just pre-made it. So when we say M is equal to 5, that means that in the global variable table, M is, unfortunately, this is like large, so I need to scroll a little bit. So this is at 1024. Right? So I'm now saying f of m. So what does f of m mean? It means the local n gets assigned m. That's the same. So that means that the local n is this guy. And gets assigned means that this gets copied. So this technically means that n and m are aliases. They're both at 1024. But it doesn't really matter because you cannot modify the contents of n or the contents of m like you would with lists. You're now saying m is equal to 6. So m is equal to 6 and m is not global. So that means that the local variable m is equal to 6 at 1056. And you're now saying n is equal to m. So the rule is you copy this address here to this address here. So you copy 1056 to over here. Intuitively, this just means that you set a local variable m to 6, and now the local variable n is also equal to 6. All right? So we're now printing m. What does it mean? We're printing the global m because this is a function that the local m here is gone. This whole thing is, in fact, in some sense, gone. And we're only talking about the variable table here where m is still 1024, which is still 5. Make sense? And it is, by coincidence, 5 o'clock. So I will see you on Monday. Have fun with whatever it is that you have planned for the rest of the day. See ya.
Oh.